When a massive galaxy grows, it does so by cannibalizing smaller dwarf galaxies. As the dwarf galaxy is swallowed, its central black hole is dragged along for the ride, surviving the merger as a distinct, dense point of gravity. This cosmological process creates a population of what astrophysicists call wandering intermediate mass black holes, or IMBHs. An IMBH is a black hole with a mass between 10,000 and 1 million times that of our Sun, placing it structurally between standard stellar mass black holes and the supermassive giants at galactic centers. In theory, these captured black holes should sink to the center of their new host galaxy through dynamical friction. Dynamical friction is the gravitational drag a massive object experiences as it moves through a sea of stars and gas. But for black holes lighter than 1 million solar masses, this drag is incredibly weak, causing their orbital decay to completely stall at kiloparsec scales. Stuck in the outer, gas-poor regions of the galaxy, these wanderers are starved of fuel. They lack the mechanisms to shed angular momentum from whatever sparse gas is available, keeping their Eddington ratios below 1/10,000th. An Eddington ratio is a metric that compares a black hole's actual accretion rate to the theoretical maximum rate at which it can consume matter. Because they accrete so little material, they emit virtually no radiation. They cannot be detected as active galactic nuclei, the brilliant beacons usually powered by feeding supermassive black holes. The math of hierarchical galaxy formation leaves a strict mandate. Massive galaxies must be filled with thousands of these wandering intermediate mass black holes. Yet because they are completely dark, standard observational techniques miss them entirely. That observational deficit changed with the detection of highly specific light transients, off-nuclear tidal disruption events, or TDEs. A TDE occurs when a star passes too close to a black hole and is ripped apart by its extreme gravity. Astronomers recently captured several of these events, including sources like 3XMM J2150-05 and EP240222A. When a wandering black hole shreds a star, the resulting debris forms a temporary accretion disk. This disk heats up and emits a brilliant flare of X-ray and ultraviolet light, briefly circumventing the black hole's standard low accretion invisibility. This is a map showing the spatial distribution of the 4 known off-nuclear TDEs. We can see the parent galaxy halos represented by the large vector boundaries, and when we plot the exact coordinates of the sudden light bursts, they all sit distinctly off-center within massive early-type galaxies. Because astrophysicists can model the multi-wavelength light from the disruption, they can directly calculate the mass of the hidden objects. When we scale the measurements, every single one of these off-nuclear black holes falls cleanly into the predicted intermediate mass range of 10,000 to 1 million solar masses. 2 distinct demographic trends emerge from this data. First, every event occurs in a massive host galaxy. Second, the black hole's distance from the galactic center strictly correlates with whether or not it is surrounded by a detectable cluster of its own stars. These brief stellar disruptions provide the direct physical evidence required to validate the spatial and kinematic distributions mapped out by high-resolution cosmological models. To understand how these black holes actually move after their host dwarf galaxy is captured, researchers turn to the TNG-50 simulation framework. TNG-50 is a high-resolution cosmological model that tracks the formation and evolution of galaxies, allowing scientists to monitor star clusters acting as intermediate mass black hole proxies during merger events. The simulation reveals a clear primary trajectory. Approximately 87% of all captured intermediate mass black holes slowly drift inward, sinking toward the gravitational center of the Milky Way-like host. This line chart plots the radial distance of sinking black holes against a massive timescale. The data tracks a gradual descent spanning over 10 billion years. At the 10 to 13.8 billion year mark, the curve flarbies out. The orbital decay functionally stalls. The median radial velocity for these sinking objects is incredibly slow, clocking in at negative 0.44 comoving kiloparsecs per gigayear. The simulation data confirms that this creeping velocity is constant, regardless of how heavy the black hole is. The sinking speed has virtually no dependence on the mass of the black hole itself. The physics governing this extreme deceleration point to a linear drag force. This physical model, represented mathematically as negative BV, applies when an object moves slowly through a relatively smooth, non-turbulent medium of gas and stars. This scatter plot compares sinking velocity against radial distance. Drawing an empirical fit curve through the data points maps how this drag forces deceleration. The radial velocity's magnitude aggressively declines as the black hole nears the galactic center, losing almost all inward momentum. This sudden deceleration follows strict mechanical rules. The linear drag model mathematically mandates that as the inward velocity drops, the wandering black hole's orbit must circularize, trapping it in a stable ring deep inside the main galaxy's halo. While settling into this circular orbit, the black hole is not alone. It carries a dense cluster of stars from its original dwarf galaxy. But as it moves through the main galaxy's extreme gravitational gradient, those surrounding companion stars are sheared away. The main halo exerts immense tidal forces. Over billions of years, it systematically strips the wandering black hole of its bound stellar population, until nothing of the original dwarf galaxy remains. The severity of this tidal stripping correlates directly with the black hole's decreasing halocentric radius. The further inward it sinks, the more stars it loses. This theoretical stripping constraint maps perfectly onto the observational demographics collected from the 4 known off-nuclear tidal disruption events. The disruptions that occur at large distances from the galactic center are still surrounded by detectable dwarf satellite clusters, retaining roughly 10 million solar masses of stellar material. In direct contrast, the events occurring closer to the main galaxy's center exist in total isolation. Their original host stars have been entirely stripped away over billions of years of orbital decay. Astronomers refer to these inner radius disruptions as naked TDEs. They present zero-resolved stellar light above the smooth background glow of the parent galaxy's halo. The presence or absence of a stellar counterpart acts as a direct, observable clock, measuring exactly how far a wandering black hole's orbit has circularized into the host galaxy. Beyond the lost stars, we have to look at the kinematics of the local gas to understand how these black holes might feed in the future. The gas environment determines their baseline accretion potential. This chart plots the velocity distribution of wandering intermediate mass black holes relative to the galactic center. The broad Gaussian curve shows absolute speeds near 180 kilometers per second. However, for black holes orbiting within the inner 5 kiloparsecs, the variance widens significantly. Measuring these same black holes against their local gas frame forms a sharply skewed distribution, weighted toward a much lower mean of 88 kilometers per second. Overlaying the curves reveals their velocity relative to the gas is roughly half their absolute velocity. The gas in the inner 5 kiloparsecs is moving incredibly fast, mechanically driven by the immense gravity of the main galaxy's central supermassive black hole. Caught in that central gravitational pull, the wandering black holes are moving significantly slower through their local medium than their sweeping galactic orbits suggest. To calculate how much gas these slow-moving black holes can actually consume, physicists use a theoretical framework called advection-dominated accretion flow, or ADAF. ADAF is a model that describes how black holes feed in low-density, low-radiation environments, where the energy from friction is carried into the black hole rather than radiated away. In both ADAF and classical Bondi accretion models, the rate at which a black hole captures material scales inversely with its relative velocity. The slower it moves through the gas, the more it should be able to accrete. We can apply the simulation's relative velocity mean of 88 kilometers per second to these accretion formulas to calculate their expected baseline radiation. The results confirm the invisibility problem. Even with the favorable lower relative speeds, the environment is just too gas-poor. The total accretion rate guarantees the black hole remains well below the detection thresholds of active galactic nuclei. Without the sudden, violent mass influx of a completely disrupted star to provide a temporary burst of fuel, these wandering black holes remain permanently dark. Over cosmic timescales, the innermost of these black holes will eventually sink all the way to the galactic center, merging with the supermassive black hole. This will produce powerful gravitational waves, signals that future space-based interferometers are designed to capture. Until future gravitational wave detectors launch, researchers must rely on the rare light of dying stars. The perfect alignment between the observed off-nuclear tidal disruption events and high-resolution kinematic simulations has finally unmasked the hidden population of dead dwarf galaxy engines wandering through our own universe.